There you go. So I'll just share my screen. Can you see my screen?
I can.
All right. Look at page 10. Lord, I always misplaced the pen of mine. Okay, here it is. Here it is. Okay, have a look. So I define a function f of x. You can read it, right? F of x.
Yeah.
Okay, I define that as sine
I can't
x.
see the f of x side. Can you raise?
I'm sorry, your voice is
I can
breaking
see
up.
f of x side.
You can see it?
I can't see the f side. I can't see the whole screen. Really zoom out or anything is possible. I'm not sure. You can say it. I mean, if I can get it, I'll do it.
What can you see?
I can see equals to sin x plus x by 7.
Oh, okay, that's weird. It's only showing you a section of my screen. Wait. Skype. You sure you haven't zoomed in on a certain section of my screen? I mean, try zooming out. Should be showing my entire
Trying
screen.
to zoom out. Okay, now it is.
All right. So you can see the entire thing.
Yeah.
Okay. Just tell me if you can't see anything. All right. So this is my function f of x, and I define another function. I'm sorry. You've done inverse trigonometry, right?
Yeah.
Okay. I define g of x as tan inverse of x. You cool?
Yeah.
All right. So now, what I'm going to do is I'm going to say f of x. All right. I'm going to phrase this a little differently. Let f of x have roots x0, x1, x2 through xn. Okay?
Yeah.
All right.
After this.
Then I want the summation of k is equal to 0 to n, the integral of x sub k to x sub n minus k of tan inverse x times the integral of 0 to x tan inverse k dk dx. That's my question. You still there?
Yeah.
All right. So, I mean, yeah, that's the question. And again, I'm sorry, I wasn't framing it with you in mind.
Yeah.
So, I
Hmm.
mean, have a go at it. Have you got a question for me?
No, I do, but we can alternate and then make the approach.
Yeah, sure.
If you can give me like you can start with the solution and then we can because I'm not able to get how we can start it. So if you can start and then we can start discussing what our approach is.
Okay. All right. So, all right, we've been given this function, okay? Now, actually, the little problem with this is I actually spent quite a bit of while trying to figure out this exact coefficient of x so that it actually makes the question a bit easier to solve. I wasn't able to find one, but let's try solving it using this, yeah? Okay, so we want to
Yeah.
find the number of roots first. I mean, the number and the nature of roots of this function f of x. So let's just write it down. Sine x plus x by 7. Now, the first thing I do to find, to go about finding the roots of this is to take its derivative, right?
Yeah.
F dash of x is equal to cos x plus 1 by 7. So,
Correct.
and if we are setting this to 0, cos x would be equal to negative 1 by 7, right?
Yeah.
So this function is going to have a root. Not necessarily going to have a root, it's going to have a minima or a maxima whenever this whenever the cosine of x is equal to negative 1 by 7, right?
Can you repeat that? There was some connection issue.
Oh, I didn't do much really. I just took f of x. I took
Now,
its.
after cos x equals minus 1 by 7, what do you say?
Yeah, I just said this function f of x is going to have a maxima or minima point whenever this condition holds good.
Okay.
Okay, so
And for that, you can take the second step.
no, I don't really think we need to do that. You could. I haven't really explored that path. My point is, if we could try and draw a rough graph of sine x plus 7 to get a rough idea of the type of roots we'd get. So a vanilla sine x graph would look something like this.
But it would be raised by x by 7.
Yeah, no, not everything. It would be gradually raised, right?
Yeah.
So it would. So initially, it would go around looking like x by 7, but then slowly but surely, it would start raising itself.
Yeah.
So the point is, we're only going to have a certain number of roots here. After some point, the x by 7 term is going to take over, and you're not going to get any roots.
Yeah.
Okay. And another really nice thing you can notice about this function is that it's an odd function. I presume you know what that is.
Odd. Yeah. Your odd function.
It's an odd
Correct.
function. That means it's symmetric about the origin.
Yeah.
So if we find the number of roots for it on the positive x side of the graph, we can mirror the same thing on the negative x side and say that we'll have the same number of roots, excluding the zero, obviously. If we exclude the zero root, right, and say for example if we have 1, 2, 3, 4, 5, 6 roots on this side, we'd say we'd also have 6 roots on the other side. So in total we'd have 6 plus 6 plus 1, 13 roots.
Yeah.
Okay. So another really cool point I'd like you to notice here is that since it is an odd function, not only will we have the same number of roots on both the left and right side of the equation, the actual value of the root will also be the same. For example, if this just went away on the other side and did this, I think you'd agree that, I mean, of course, this would actually bend down on the side, right?
Yeah. Yeah.
But the value of this and the value of this would be the same. So with the value of this, and my diagram is a bad one. Okay, I'll actually go away and show you the Desmos graph of it. Right, okay, I'll take this off, We can see Desmos, right?
Yeah.
Okay, so if I took this one, that's the problem statement, you can see that it behaves pretty similarly to what I drew. And since it's an odd graph, these values, this minus 3.698, this plus 3.698.
Yeah.
The actual values of the roots are also symmetrical. And so will be the case for this root and this root. And you can see that in this specific question I framed, you only get 5 roots. After that, the function just shoots up to infinity and negative infinity on the other side.
Yeah.
So we only get 5 roots. Of those 5 roots, one of them is a 0, right? And the other, and from there you can go in pairs, right? These two are plus and minus something. These two are also plus and minus something. Got it?
Yeah.
Okay. So, wait 1 second. K is equal to 0 to n xk. Okay, go this and this. Right, yeah, I think it's good. Okay, so we got a vague idea of the roots of this function, right? So
Yeah.
and we also know for another fact that the number of roots will always have to be odd, right?
Yeah. Yeah.
I mean, I don't have to explain that, right? It's quite intuitive.
Yeah.
So, for
One
example,
on
in
the other
this,
side, x on the other, like some amount on the other side, and another amount on the other side, plus the origin.
yeah,
Right.
so you'll have something times 2 plus the origin. So always odd.
Yeah.
So in this case, we have 5 roots. So I think I could just express that at this point as x0, x1, x2. I mean, in an exam, you'd have to calculate this manually. That's why in order to have a neat value for this 1 by 7 c, so you can calculate the inverse of 1 by 7.
Yeah.
If you can do that, you can easily reason the number of roots that you would have. Even in this case, you can, but it'll require some amount of manual calculation. But we have a graphic calculator to aid us in this specific instance. 0, 1, 2, 3, 4. Okay. So
Yeah.
let this be of 5 roots, and they're also symmetric. So the x1 is equal to the negative of x3, and x0 is equal to the negative of x4, and let x2 be equal to 0. Okay?
Yeah.
Okay, and I also forgot to mention these are arranged in ascending order, x1, x0 through xn. Okay, so now that we have that, we need to compute this horrendous looking integral. But frankly, it's a pretty easy one. So if yeah, let's just clear this out. Yeah. So we have tan inverse x, right?
Yeah.
And tan inverse x, assume you're privy to the graph, it looks something like that. Very similar to the
Yeah.
sigmoid function. Yeah.
Yeah.
And also notice tan inverse x is also an odd function.
Okay.
Yeah, it's symmetrical about the origin. And a neat property of odd functions is that when you take the integral starting from 0, right, they usually yield an even function. No, usually actually it's a property. They always yield an even function.
Okay.
So you'd get something like this, right? When you take its integral. And this is frankly kind of intuitive. One way I'd explain it is, for example, I'm drawing a parabola like curve here, but it's not going to be a parabola. if you if you start taking its integral this way, right? Then you'd get a certain curve, right? Whatever be that curve, it doesn't really matter. The only thing is,
Yeah.
you are doing the same thing, essentially the same area on this other side, but it's going to be negative, right?
Yeah.
But since you're going in the negative x direction, you would have to flip your sign.
Yeah.
So essentially getting the same graph but flipped over the x-axis, but then you're flipping it again, right? So you
Yeah.
get this essentially the same graph mirrored over the y-axis.
Okay.
And that's the
Yeah.
definition for an even function, right?
Yeah.
Okay. So essentially what this is, we don't even have to solve this integral. So all we have to do is say that it is even. Yeah, you'll realize why we don't have to solve it in a moment. This is odd, right? Like a
Yeah.
question for you. What do you think happens when you multiply an odd function with an even function?
It should get zero as far as I'm thinking, but I'm not sure.
What did you say?
Not zero, maybe not zero or some kind of value
No,
which
it
is
is definitely going to be another function, yeah. As specifically, I'm asking you to comment on the nature of that function. Do you think it'll be odd, even, or none?
you're multiplying order than even, then it should be even.
I'd ask you to think about that again.
In the case of numbers, that would work, but with a function, then it's odd, most probably.
Yeah, I mean, look, the odd function. Think about it this way. Let's just first take a function in the first quadrant, right? An odd function is basically this mirrored over the y-axis and then mirrored over the x-axis, right?
Yeah.
You mirror it twice. First you mirror it like this, and then you mirror it like this, right?
Yeah.
And an even function, what happens is in an even function, you just stop at the first mirroring,
Yeah.
right? So the point is, for an even function, f of x is equal to f of minus x.
Yeah.
And for an odd function, f of x is equal to the negative of f of minus x.
Okay.
You see that? It's pretty intuitive, right?
Yeah.
Okay.
Yeah.
So let's say we've got two functions in multiplication, f of x and g of x, right? And let's say this is pretty similar to what we've got here. You can consider this here f of x and this here g of x, right? And we know for a fact that f of x is odd.
Yeah.
We also know that g of x is even, right? Now let's try plugging in f of minus x, right? And by definition, if f of x is odd, then f of minus x will be minus f of x, right?
Yeah.
So if you substitute x with minus x, you'd get minus f of x. And in g of x, if you substitute x with minus x, you'd get f of g of x itself. No change, right?
Yeah.
So this, let's
Yeah.
call this function h of x, this combined product, and this is h of minus x. Any idea now?
If that's a minus x, then that would be an odd. Yeah.
Yes, so we can say that h of x must be an odd function,
Yeah.
right? So this entire thing is an odd function. The thing we're taking an integral of,
Yeah.
that is an odd function, right? Okay. So
Yeah.
from here it's pretty easy. You know, wait 1 second. That's becoming pretty inefficient. Just lasso this thing. Oh, okay, wait. Yeah, that's gone. So now we're essentially taking the integral of an odd function times dx. Yeah. Okay. So now here's a interesting thing about an odd function, right? Let's just consider an odd function, I don't know, like a cubic. Not drawing it perfectly.
Yeah.
Okay, that's an odd function, right? A cubic, certain cubics are odd functions. For example, you might consider this to be x cubed. So now, if I take the integral, you know that the integral equates to computing the area under graph, right?
Yeah.
Okay. And now consider a specific case in this. Consider I'm always computing the integral of x cubed dx from some constant negative k to some constant positive k. Would you comment on this integral?
This integral is basically the summation of all the areas. If you're taking like from whatever from the minus x side, all the areas which you're combining to give till k.
Yeah,
So x
so
cube, you
for
so
example,
yeah.
assume k is, for example, 2 and 2 lies somewhere here. So this would be positive 2 and this would be negative 2. And this integral is basically computing this area. What do you think that the value will be?
Mhm. Since area can't be negative, like
Area can
there'll
be
be two of
negative.
that.
Wait, if you're not privy to this, area under a graph below the x-axis is treated as
Um,
negative. For example, if I had a sine x graph, this would be positive area, this would be negative area. Now tell me.
okay, then it's zero,
Yeah, and it's
which
always
means the whole
0, right? Because it's an odd function. It's symmetric about the origin. So, for example, if I had some k here, right, this
yeah.
this value tending to whatever that value is, and if I had minus k here, at this value, the magnitudes would be the same, and that's valid for every point. So
Okay.
if you do compute that integral, since it's symmetric about the origin, and you're going from minus k to plus k, the same distance from the origin, on the negative x-axis and the positive x-axis, it's the area you're taking is symmetric and of opposite signs, so 0, always, regardless of the value of k.
Yeah.
Okay, so that's an interesting property. I kind of missed out when I was taking my integrals class, and I screwed up on it on an exam. It's a really important thing to know. Right, so we're taking, so essentially why I focused on this integral from minus k to plus k is because the nature of the roots we got really resemble that, right? We've already
Yeah.
determined that x1 and x3 are just negatives of each other, and x0 and x4 are negatives of each other, right?
Yeah.
So essentially, what I'm saying is, if we take k to 0 is equal to 0 to n, we basically get a bunch of integrals, right? So x0 to x4, right? Yeah, x0 to x4. The first integral we get is x0 to x4 if you open up this summation. I'll just write this entire function as I don't know, v of x for the lack of a better name. V of x dx, right? And then to that we add the other integral, x1 to x3 v of x dx, and to that we add another
Yeah.
integral. This goes from okay, you get x2 to x2 again, v of x dx. You wouldn't stop, you'd go on, you'd get x3 to x2. Oh, actually, that's gonna make the problem a lot easier. No, 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 don't consider that. Just say it's still, I don't know. n by 2 here, floor. Okay.
Okay.
So since we have 5, no, I took that off because eventually if we kept going, you'd get values like x3 to x1. So that would just entirely cancel this integral out, so regardless of what you
Exactly.
get here. I mean, that would be a very easy question. So don't take it till n. Take it till n over
Okay.
2, the gif of that. Okay. So if you do that, we just get these three integrals, right?
Yeah.
Okay. And now we already know that x0 and x4 are opposite in signs and have equal magnitude, right? We also know
Yeah.
that v of x is a knot function. So what do you think this becomes? 0. And by
0 because
similar logic, because x3 and x1 also share the same property, even this becomes 0. And this by default is 0 because both the limits are the same.
yeah.
The final answer is 0. Well, that's the solution.
Okay.
So where have you got?
Okay. That's my turn. So there's a function f, the fx defined on the set of positive integers,
Okay, so there is a function fx defined on the set of positive integers. Sure.
and f1 is f of 1 equals 2016,
F of 1 is equal to 2016.
and for all n greater than 1,
Hmm.
f1 plus f2 till fn is n square into fn.
F1 plus F2 plus whatever F3 till Fn is equal to
N square into f,
n square into.
fn, f of n.
Oh, okay, n square into Fn. All right. I'm sorry, it was just cracking. Could you mind coming again?
F of 2016 is a just to be calculated. F of 2016.
Okay, you need me to calculate F of 2016.
Yeah.
Hmm. Well, F of 1 is 2016. And the summation of all f of n to that is equal to n squared times f of n. Alright. So basically what you're saying is if we just plopped this f of n over to the other side, we'd get f of 1 plus f of 2 plus f of 3 till f of n minus 1 is equal to n squared f of n minus f of n.
Yeah.
Okay, so we get f of n times n squared minus 1. Alright. So the summation is equal to f of n times n squared minus 1. And you need f of 2016. And we know f of 1. I'll just write this in a way that I feel more palatable. F of 2, f of 3, all the way till f of n minus 1. Basically the sum of all the previous terms divided by n squared minus 1 is equal to the next term. Okay. So if you followed this and, I don't know, computed f of 2, what would you get? You get 2016 divided by 2 squared minus 1, that's 3. You'd have f of 3 to be 2016 by 3 times... Oh wait, not just 2016 by 3, my bad. 2016 plus 2016 by 3. All of this divided by 8. and you'd get f of 4. I'll just write the fourth term. I think it's going to be too excessive after that. 2016 plus 2016 by 3 plus 2016 plus 2016 by 3 by 8. All of this divided by 15. Phew. Okay. So,
Maybe we can obtain some form of reference relation just to help you. We can obtain some form of reference relation.
that's what I initially intended to do, but
You're moving on the right path. You just like if you look at the
yes.
first function, f1 plus you can the whole numerator can itself be written as n minus 1 whole square into f of n minus 1, right?
The whole numerator can be written as n minus 1 whole squared times f of 1.
F of
Oh,
n minus 1.
fn minus 1. You're saying this can be written as f of n minus 1 whole squared times f of 1.
No, not that way. I'm saying, look at the rule given in the question is f1 plus f2 till fn is n square fn, right?
Yes.
So if you just move one step back, you'll get f1 plus f2 till fn minus 1
Okay, so
is.
yes, okay, sorry, I shouldn't have to interrupt you. What are you saying?
So basically, like if you see the rule of the question, f1 plus
Yes.
f2 till n is n square of into f of n. So if you take that till n minus 1 instead of taking it to n, then you'll get on the right hand side n minus 1
I
whole
see
time.
I see where you're going. So you're saying f of n minus 1 here, whatever, is equal to n minus 1 whole squared times f of n minus 1. Alright, plug that in here. Ah, okay, alright. No, not, they don't exactly cancel, but sure. F of n minus 1 times n minus 1 whole squared times n squared minus 1 is equal to f of n, right? So that's f of n minus 1. Okay, you'll just have n minus 1 here, you'll have n plus 1 here. That's equal to f of n. Alright. So you're saying, I'll just rewrite that in a different way. N minus 1 times n plus 1 times f of n minus 1. So 2016. And 2 would be 2 plus 1, 3, 2 minus 1, 3, 2016. And then you'd take this, right, and then multiply it with. Okay, so basically, if you start with 2016, you just continuously keep multiplying it with 1 by 3. Then, well, that was for 2, and then you'd go 2, 3, 4, right? Then you'd go 3, 4, 5. Then you'd go 4, 5, 6, something like that. And you'd have to take this all the way to, what did you ask for? 2016, 2015, 2016, 2017. Alright, I see a lot of terms cancelling here. 3 and 3 would cancel, 4 and 4 would cancel, and just like that, you'd have only the first two terms remaining here. I'd suppose you'd have the last two terms remaining there. So essentially, in the end, you'd end up with 2016 times 2 divided by 2017 times 2016. Is it 2 by 2017?
Yeah, it's 2 by 2017.
Yeah. I slipped up a bit in the beginning, but thanks for the hint.
Okay, your next question.
Okay, look, Riddles only gave me an hour, and I spilled the entire hour on that one question. I don't know, how many have you got?
I have about 7.
7?
Yeah, 7.
Oh, 7.
But all are of the same kind of, you could say, elementary degree. Not they are difficult, not that easy, but They'll have just this much of thought into this, and then we'll be at the answer.
I see. Right. So
We can do like 2 or 3 more till we're done.
yeah, sure. I suppose we can make that work. Let's see. Go on. Next question.
Okay, we have a function f of x which is equal to ax plus b,
X plus B, sure.
and g of x which is equal to bx plus a,
G of X is equal to BX plus A.
where a and b are both positive integers.
A, B are both positive integers.
Find ab if FOG 50 minus GOF 50 equals 32.
FOG 50
Yeah, minus GOF 50,
is equal to
36, 36.
36. FOG 50 minus GFF 50 is equal to 36. Alright, I suppose you can just compute f of g. F of g.
Actually, make that the maximum value of AB if FOG 50, the maximum value of AB. You missed that part when I was writing the question.
Okay, maximum value of AB if that is the case. Alright, f of g of x is equal to a bx plus a. Bx plus a squared plus b. Okay, so you're plugging a linear function into another linear function. You should get another linear function. That makes sense. G of x of a would be just b times ax plus b plus a. That's a bx plus b squared plus a. Now you're saying this 50 minus that 50. Well, if you did plug in 50 here, you'd get ab 50 plus a squared plus b. If you plugged in 50 here, you'd get ab 50 plus b squared plus a. So you subtract these, you'd get a squared plus b minus b squared minus a is equal to 36. So you essentially got a quadratic relation, but not exactly quadratic, 2-degree relation between a and b. b minus a, that cancels out. Whoops, that cancels out.
I think you made a mistake over there. That's little away. A minus B to A plus B of B minus A. How do you put that inside the bracket again? Wouldn't that come as 1? Like if you think about it.
Oh wait, what did I take common? Okay. Thanks for pointing that out. Okay, a minus b would come out. You'd get a plus b. B minus a, that would be minus 1. Yeah, sure. So this product is equal to 36. And you want the maximum value of AB. And you also said that there are integers.
Yeah. Positive integers.
Yeah, right. I think we can solve this using simple factorization. What do we have for 36? 18, 2, 9, 4. Probably 6, 6. 3, 12. Yeah, I suppose that's it.
There is one more.
Oh yeah, there's one more. What did I
The
miss?
basic 1 into
Oh,
36.
1 times 36. Yeah, of course. Alright, 1 times 36. Oh, come on, do I have to solve 5 equations now? Bet there's an easier way to do this.
Not necessarily. There's like if you look at the properties of what is inside the bracket and what their range be.
Understand what you're saying. So, since both of these are actually positive integers, then you can argue then that, okay, you have a minus b, you have a plus b minus 1. This would always have to be less than this. But does that minus 1 too? Yeah, no, this has to be less than that, even if b happens to be 1. Okay. So where do we go from that? So the values that a... wait. So the values that this and this can take are actually reduced to 2, 18, 4, 9, 6, 6,
You
probably
can't take 6.
12. Oh yeah, yeah. Nice thing to find out. We can't take 6, 6. 4, 9, 3, 12, 1, 36. Alright, from this point, I think we can easily solve it. A minus b is equal to 2, a plus b minus 1 is equal to 18. What do we get? A is equal to b plus 2, so 2b plus 2 minus 1 plus 1 is equal to 18. This has no positive solutions. A minus b is equal to 4, a plus b minus 1 is equal to 9, so that's 10. So a is equal to b plus 4, so 2b plus 4, that's 10. That's 6. B is 3, right? And what will that give you? A as 7. Wait. Yeah, okay, so that's fine. 7 and 3, that give you a b is 21. That's one of our options. And if we have a is equal to 3 plus b, then you have 2b plus 3 minus 1 is equal to 12. This gives you 2, this gives you 10, this gives you b is equal to 5, b is equal to 5, then a will be equal to 7. That's obviously not counted. If we have a minus b is equal to 1, then a...
Should be 7.
What?
Plus b.
Oh, you asked for
Should be
minimum?
7.
Minimum or maximum? Oh, maximum. Yeah, my bad. Alright, that'll be 35. Sure. Yeah, and then...
You you wrote a equals 3 plus b. So how is a 7 if b is 5?
3 plus b, whoops. That makes sense? Yeah, that does make sense. Times 5, 40. Skipping up a lot, am I? Yeah, fine. And then we have 1 plus 36. A is equal to... plus b is equal to 1, 1 plus b. So 2b plus 1 minus 1 is equal to 36. Pretty sure this is going to get us nowhere. B is equal to 18. Then A is equal to 17. Okay, 35. Sorry, 40. Is that the answer?
I mean, a equals 17 and b equals 18 is the maximum product if you think about it.
Oh, sorry, you're
Maximum.
asking the maximum product. I keep forgetting that. Okay, whatever the product of these, with the 17 times 18, that one.
Yeah.
That's my answer. Okay. Didn't intend this to be as one-sided as it has become.
Maybe the penultimate, or we can come to the second last or last question. We can. I have 2, 3 more. I have a few.
Okay, give me the hardest
So
one you got.
yeah. Okay. So we have a function fx divided f divided not divided uh, limited to real numbers where f of x into f of y equals f of x plus y plus xy.
f of x plus y plus f of xy. Is this right?
Not f of x, just xy, plainly xy.
Oh, I'm sorry. Could you repeat the RHS again?
F of x into f of y equals f of xy plus xy.
Okay, f of xy plus xy.
No, f of x plus y plus xy.
Oh, okay. F of x plus y plus xy.
Yeah, fine. We have to find fx.
Okay, we have to find f of x. Alright, so let's see. If we substitute x everywhere, what do we get? F of f squared of x is equal to f of 2x plus x squared. And f of x times f of y. Oh, f of x plus x, but that's not going to get me anywhere.
Maybe taking something as zero would help.
What?
Maybe taking one of the variables as zero.
Sure, you could try that. Wait, let's try this. F of x by 2 is equal to f of x plus x squared by 4. Okay, but then again, we'd be solving. We have f of x by 2, then f of 2x, then f of x in the middle. Alright, let's see where what you say telling me takes me. F of x plus 0. Interesting insight. F of 0 is 1.
But I mean, you didn't. You cancel the possibility that fx can also be zero, because this we can't exactly cancel fx out if you think about it. Maybe it'll have to be proved to be zero, or it can have a value of zero fx, or like you can't directly say f of zero equals one if you think about it.
Fx is, if fx is equal to 0, then f0 can be anything. Yeah, but then isn't that wait, f of x would have to be 0 for some value. If it is, then f1 would not have to be. Okay, here's my argument. If f of x takes up any value other than 0, if it ever
Yeah.
does, then this will have to hold true.
Yeah.
Otherwise,
Okay.
if f of x is a constant function of 0, then by definition f of 0 would be 0. So I mean it would be a constant function, right?
Yeah.
Right, so that's one possible answer we have. But then again, we'd have to consider the other scenario, right? Okay, so we
If
have
you have taken,
what?
what if you think about it this way? If you would have taken
Sorry, your voice clipped out.
f of 2 plus 1, f of 1 equals f of 2 plus 1 in the sense that, so f1 whole square. So let's say we were taking f of 1 whole square equals f of 2 plus 1. Then we would have gotten that 0 equals 0 plus 1 would have been a fallacy in our consideration if you think about it. That's why that's an argument to saying why fx equals 0.
So if you say
F square.
f of 1 is equal to f of 2 plus 1, what did he say the fallacy is here again?
like if we have to prove why fx cannot be taken as zero. So in this
Yeah,
case,
yeah, sure.
we would
Right.
have gotten this
You can say that
plus one.
this equality proves that f of x cannot be a constant function equated to zero. Right. Interesting. So if you did that, then f of 0 will have to be 1. So if you do plug in f of 0 here, I'm curious, what do you get? You get 1 is equal to 1 plus 0. Okay, that checks out. Hmm. Okay, so now we've got to somehow use that to derive possibly something else. Okay, let's try this. F of 1 times f of 0 is equal to f of 1 plus 0, right? So we get f, okay, f of 1 is equal to f of 1. That isn't really helpful, is it? Yeah, you continue to get that if you take any constant value.
What if you would try taking something like, in such a scenario, you get to a point where the right hand side somehow becomes zero. Thinking about that way.
So the right hand side becomes 0. F of x plus y should be equal to xy. Alright, so if you took something like, I see where you're going. F of 1, f of minus 1, f of 0. Okay, no, wait. That wouldn't work out. You'd get f of 0
Another question.
minus 1. Hmm. And we do not. Okay, so I want to check what kind of a function this is. Oh, but I can't do
You
that.
can say f of zero is one. So you can get two cases if you think about it.
So either f of 1 is 0 or f of minus 1 is 0. So you always end up getting either 1 or the positive 1 or the negative 1 has to be 0. And I think if we plug in f of 1, what do we get? We get f of 1 is equal to f of 2 plus 1. So if you say f of 1 is 0, then f of 2 will be negative 1. And if f of 2 is negative 1, then what will f of 3 be? We can say that f of 3 times f of minus 3 is okay, but that argument won't exactly work there. You'd get minus 8 plus xy. Yeah, you do get minus 8. Alright, but I'm beat. Give me a hint.
Okay. So we have seen that we can come to two cases, f of 1 equals 0 and f of minus 1 equals 0.
Right?
So in that case, let us use the parent equation and plug in x to be any number, let's say p minus 1, and y to be 1.
Okay, x is p minus 1, y is 1. Alright, so you do get f of 1 plus p minus 1 times 1 is equal
Not
to.
1.
Wait, oh,
P minus 1 plus 1.
p, sure. F of p, and the rest still hold good. Okay.
Now we have already, in this first case, we have taken f of 1 equals 0. So
F of p is equal to 1 minus p. So, see, you're saying me f of x is equal to 1 minus x in the first case.
yeah, and the second case.
And in the second case, yes, you were getting if f of minus 1 is equal to 0, then you can still somehow, okay, so you can.
Instead of taking p minus 1, let's take another number, p plus 1.
Yeah, f
Like
of p
instead of
plus
p
1.
minus 1, we take 2 plus 1.
Yeah. Right, this goes to 0. So you get f of p is equal to minus p minus 1. So that is equal to minus x minus 1. Or minus 1 minus x. So basically, it's either 1 minus x or minus 1 minus x. So do you end up getting two functions, or is there any other resolving factor here?
No, that is the answer. Like if
So
you're
this
taking
is the
one.
answer. You get two
But
functions.
you know, you actually missed out. You actually missed out on something in the second case. So like the x from the parental derivative should become minus one into q plus one, which would mean minus q minus one. I mean minus p minus one. Essentially, like on the in the first case, you took f of p minus 1 into f1 equals fp plus p minus 1, which is basically p minus 1 into 1. But over here, you'd get f of p plus 1 into f of minus 1 into f of p plus minus 1 into p plus 1. Right.
Yes.
So you'll have to make that equation.
So that's what it did. You get minus 1 minus x.
No, no, no. You wrote, see, if you look back at, you have written f of p
Mm-hmm.
plus of p plus 1, right? Shouldn't that be minus? Because you're multiplying that with minus 1. You've taken minus 1 to be the y in this case.
No, I've actually written the minus of that. I wrote it after I wrote that. I was lazy.
Yeah, but when it go to the other side, it'll still become p plus 1. You wrote it as minus p minus
Oh,
1.
okay. So my bad. I get what you're saying. So 1 minus x, 1 plus
So
x.
we'll get the family of equations to be
I'm extremely sorry. Could you come again?
we have two cases, 1 and 1 plus x. So then we can write the whole thing as fx equals 1 plus minus.
What did you say? F of x is equal to 1 plus or minus x. You're saying that?
Yeah,
Okay, so that's the answer to this thing.
yeah.
Right. Really interesting.
Last question. We can do the last question for today as well. Time is getting a little.
Yeah.
So
Go on.
the last question is find f of x if f of 2x minus 5 whole by x minus 3. No, 2x minus 5 in the bracket only. No, like
I was doing
2x
it on.
minus 5 whole in the bracket.
Yeah.
And not the whole thing, not the whole thing. 2x, the bracket part divided by x minus 3, x minus 3. Yeah, equals to x square by 2.
Equals x squared by 2. Okay, so you want me to find f of x. So here's my thing. If I say 2x minus 5 by x minus 3,
We can take that to be y.
you can take this to be y. Or, okay, wait. So you're plugging in a rational linear function and you're getting a simple quadratic. Okay, let this be some g of x. Right, so we're basically saying f of g of x is equal to x squared by 2. Well, how do you say we proceed?
Instead of taking g of x, we can take y to make it a little more easier, and then replace and substitute a value of x we can get in terms of y.
Oh, okay. Alright, so 2x minus 5 is equal to yx minus 3y. x 2 minus y is equal to 5 minus 3y. Oh wait, we're solving, yes, we're solving in terms of x. Oh wait, we want this thing, x is equal to 5 minus 3y by 2 minus y. Alright, so you got x in terms of y.
And from here, plug in the value of y and then get it in terms of y and replace everything in the parent equation with y, and then we'll say that fx equals whatever we get. And then from there, it's mathematical part.
Just come again?
After this point, you can just replace every element of x in the parent equation with whatever we have gotten in terms of y, and then we'll get a whole equation in terms of y. And then we'll say fx equals whichever terms are in y, we'll replace with x to get fx. Think about it.
Okay, so you're telling me if you replace the substitution here, then you'd get something simple like f of y.
Yeah.
Huh.
So, for example, like now we're simplifying the so 2x minus 5.
Yes.
So instead of going by the whole factor, take 2x 5. If we convert that in terms of y, you can see what we get 2x minus 5. There's a new.
But I'll just stop you right there.
So we have
I
to
didn't
find
hear anything of what you said for the past 30 seconds. Your voice is really choppy.
basically what I'm trying to say is we have to find it replaced in y. So let us take 2x minus 5 for the first part. So instead of taking the whole fraction, just that value in terms of y.
Are you still speaking? Oh,
I am.
wait, understanding you is a real challenge here. So what I understood is you. Well, actually, I didn't understand anything. All I heard was a different chords and robotic kind of voice, which is frankly incomprehensible. Can you hear me? No, you're frozen.
I hope it's a little better.
Yeah, I can hear a coherent sentence. I think that's positive. Go ahead.
Okay, so instead of taking the whole fraction, let's say that 2x, let's take 2x minus 5 in terms of the new expression we have gotten in y,
Mm-hmm.
and then also find for x minus 3, and then we'll plug that into the equation and see what we get, and then replace.
Okay, so this is you just going out on a stick here. Okay, all right. So you get 2 5 minus 3y, 2 minus y minus 5. 10 minus 6y by 2 minus y minus 5. Alright, you get 5 minus 5. Wait, no, what am I doing? You get 2 minus y. Okay, 2, 10. 2 times 3, 6. Yes, okay. So, well, there's no point in taking out 2 again, it's just multiplied to 10. Minus 5. So, 10 minus 6y minus 10 plus 5y by 2 minus y. So, well, minus y by 2 minus y. Now if you plug it in here, you get 5 minus 3y by 2 minus y minus 6 plus 3y. That cancels. Minus 1. Alright, you do get f of y. So you've engineered this question such that you do get that. Alright. So that goes in.
I did like calculation were a little wrong. I mean, it wasn't that simple. The value you got 2x minus 5. What was your answer for 2x minus 5? Firstly,
2x minus 5, you get minus y by 2y minus 3.
I think there's a little defect in that. X equals 5 minus 3y by 2 minus 5, if you think about it. So On that side, we'll get 10 minus 6y
Yes.
by 2 minus y minus 5.
Mm-hmm. So
And then you'll get 10 minus 6y minus 10 minus 5y by 2 minus y.
you'd get plus 5y, right? Because you have 2 minus y. So minus y
Um,
times minus 5, you get plus 5y.
10 minus 6y, like, just a second, minus 5 into 2 minus y. Acha, okay. And then for x minus 3,
For x minus 3, you get minus 1 by 2 minus y. So ultimately, they just cancel out to give you f of y.
yeah,
So, alright. A pretty smart trick there, I should admit. 5 minus 3y by 2 minus y. That must be the answer you're looking for.
the whole square.
Yeah, the whole squared.
Okay, I think we can call it a day. Call it a day
Yeah,
now.
we sure can. Those were some pretty nice questions. I hope I had some more for you.
Yeah,
Right. See you next time. Bye.
yeah. Bye.